So next up is, again, no stranger to the WaterOnline community and to those attendees who have visited and attended the Virtual Water Expo in the past. He is an expert in the field, and he comes to us from Fluid Components International, also known as FCI. And I'd like to go ahead and without further ado, introduce my friend, Adam Schlehan. Adam, the time is all yours, and I'm going to get out of the way.
Good morning, everybody. I'm Adam Schlehan from Fluid Components International. We're a company that has supported engineers and contractors and end users in gas flow measurement in the wastewater industry for over 50 years. So measurements in applications such as digesters, all sorts of different blower applications, odor control, and flares are very commonplace to us. And one issue that we see quite a bit when we work with our customers is what happens to a measurement as a result of inadequate straight run. So there's a certain amount of real estate that's needed to get a good, accurate measurement. And when obstructions are introduced either upstream or downstream of the measurement point, or you simply don't have enough straight run, that will have an impact on the level of accuracy of your measurement. So we have some CFD models. We have some models that we've run in our application evaluation software to educate on how different obstructions and different amounts of straight run will affect your measurement. And we're also going to talk a little bit about flow conditioning, which is a solution, and the effect of flow conditioning on permanent pressure loss in your system. So moving forward here, anything that you read about in a vendors in their data sheets, in their marketing materials, any of the accuracy, the repeatability, anything that's published there assumes that you're operating under perfect lab conditions. Not necessarily what's in the real world, but in the perfect lab conditions. And what does that mean? Well, there's a few things that you see in a perfect lab that you won't see in the real world. Number one, calibration happens with clean, dry gas. You have reference meters that are more accurate than the instrument that's being calibrated. And the important thing for this conversation is that there is plenty of straight run. So here we see our calibration lab in San Marcos, California, and you see plenty of straight run in our cal lab. Now, why is the straight run important? The straight run and the adequate amount of straight run upstream and downstream from the measurement point will enable a fully developed flow profile. And that's what you see here with this turbinate and laminar flow profile. And many of the instruments that are in use today rely on a single point of measurement. And where you'll get that most accurate measurement is at the point of maximum velocity. So if you see this parabola here, that's right at the tip of the bullet, right at that high point of the parabola, making a measurement right there, which typically occurs right in the center of the pipe, will give the most accurate measurement. Now, we talked about ideal conditions and perfect lab conditions. And we see that in the real world, in the actual application, that quite often the focus is on those higher value, big ticket items, and selecting a point to make a measurement and to install an instrument can quite often be an afterthought. So quite often what we hear is, we know that 20 diameters upstream and 10 downstream is needed, but we've got this elbow, we've got this valve, we have some obstruction, and that's not possible. So I'll talk a little bit about how that will impact the accuracy of your measurement, as well as a solution that we see work quite a bit. Now, our guide, as I said, is 20 diameters of straight run upstream and 10 downstream, whether you have elbows in plane, elbows out of plane, reducers, adapters, valves. Our guidance pretty much runs 20 upstream, 10 downstream to give you the fully developed profile that you need to make an accurate measurement. Now we're running CFD here, computational fluidic dynamics, And what you see here is that red in the pipe on both axes represents the higher flow velocity, and the green and the blue represents the lower flow. Now, this is your perfect 20 diameter straight run. What you see is a very nice, fully developed flow profile. This will give you the ideal lab condition, excellent measurement that you're looking for. Looking at what a couple of things do here, and just to give a representation of modulating valves, of adapters, of elbows, what you see in these diagrams is that you don't actually get that bullet shape anymore. That those cause obstructions to the flow profile, and this will introduce uncertainty into your measurement. Now, we've said we would run a few of these. One thing that we see everywhere is elbows. Here's a situation where an in-plane elbow is installed 4 diameters upstream, and you see that it throws off the flow profile. We're much closer to the top of the pipe with that point of maximum velocity. And even a very common obstruction such as an elbow will cause 4.3% measurement uncertainty. Now, a little bit more benign, but still thought it was worth mentioning, is that it's not just elbows and obstructions upstream. The same will apply downstream. Introducing an elbow 2 diameters downstream, it'll cause a more benign and perhaps a more acceptable measurement uncertainty, but still introduces almost a 1% additional impact on your accuracy. Now, getting into some more of the things that we see that continue to cause issues, a convergence, 4 pipe diameters upstream causes a 1.3, maybe perhaps not the worst. But when you see items such as the butterfly valves, now that really does create a significant impact on the flow profile that will have a much more significant impact on the accuracy of your measurement. In this case, 5 diameters upstream with a half open butterfly valve will introduce 15% additional uncertainty into your measurement. The same butterfly valve downstream, 1.7. So again, more benign, but still worth mentioning. Now we've introduced both. So what happens if you have a convergence 7 diameters upstream, a butterfly valve 4 diameters upstream, and an elbow 2 diameters down? You'll see that it really throws off the flow profile. It creates a situation where you're simply not able to make a good, representative, accurate measurement of what's going on. And that has an 18% impact on your measurement. So one thing that we have in addition to the CFD models that we've been going through is our application evaluation software. Based on all of the data that we've accumulated over the 50 years that we've been working with our customers, we have a pretty good understanding of how different obstructions and different levels of clearance upstream and downstream will impact accuracy. So a butterfly valve upstream will introduce a 9% inaccuracy in certain situations. And we could go through these, but the point here is that if you use a flow conditioner, typically something that is installed upstream of where the measurement is made, that will help to create a more uniform and repeatable and consistent flow profile that can help to alleviate and eliminate some of the uncertainty that is introduced by the obstruction. So going back to the initial model that we had of the butterfly valve, where we had the 8.76% uncertainty without flow conditioning, installing a flow conditioner 3 diameters upstream will bring that from 8.76% uncertainty down to a much more acceptable 1.04%. So the idea of a flow conditioner that you see here, in our case, it's the FCI VIP plate. is it gets installed 3 diameters or 4 diameters upstream. It depends on the application. And all the eddies and the swirl and all the turbulence that's introduced into the flow profile is conditioned, and the flow becomes a more consistent and more uniform and more repeatable profile to measure, which enables an accurate measurement, especially if the instrument is calibrated with the flow conditioner. So applying the flow conditioning to our nightmare example here with the butterfly valve and the convergence in your flow stream and the elbow downstream. Remember, this was 18% uncertainty introduced. This was the worst case. It essentially destroyed our flow profile for a good measurement. With a flow conditioner in this application, it brings the uncertainty from 18% down to 0.8. So you could really create a much better condition for an accurate measurement in those tight quarters with a flow conditioner. So the installation, as I said, is important. A good manufacturer will calibrate the instrument with the flow conditioner in the cal lab to give that good representative calibration of what it will look like in the application. But really, what I want to talk about in addition to the flow conditioning is that not all flow conditioners are created equal. A flow conditioner will introduce permanent pressure loss into your system. And just to give an example of what that will look like, our instrument without a flow conditioner at 5500 SCFM, ours is an insertion style, will introduce 0.08 PSIG of permanent pressure loss. Now that's negligible. Looking at what you would get with our VIP plate, in addition to that adds about another 0.5 PSIG for a total permanent pressure loss of 0.61 PSIG. And what you'll see is that if we're 0.08 PSIG from our meter in the flow stream of pressure loss, and we're overall 0.61, the bulk of that permanent pressure loss with any instrument and any flow conditioner will come from the flow conditioner. And as I said, not all flow conditioners are created equal. In our case, in that upper left corner, you see our Vortab VIP plate that we calibrate our instruments with that are intended for use with FCI flow meters. But there is a multitude of different flow conditioning technologies that are out there. Your screens, your tube bundles, there are certainly different options that are out there, and each option does come with a different amount of permanent pressure loss. So what does that look like in the application? As I mentioned, the VIP plate, we're looking at about a 0.5 PSIG permanent pressure loss, and the different options that are available from different manufacturers will run anywhere from our 0.5 all the way up to about a 5.23 PSIG permanent pressure loss. So the type of technology that you use for that matters. Being sure to calibrate the instrument with the flow conditioner matters. And there are different levels of pressure drop with the different flow conditioning options. So what I talked about today, wrapping it up, there's two issues here. One is the inadequate straight run. 20-10 is ideal, 20 diameters upstream, 10 downstream. If you don't have that, no problem. Let's use a flow conditioner, and that could knock down your measurement uncertainty from as high as 18% down to 0.8% in certain applications. And the second point here is not all flow conditioners are created equal. Calibrating with the flow conditioner is important, but even more importantly, a consideration is that permanent pressure loss, and different flow conditioning options will have different levels of pressure loss. So that's my presentation here. We have more options available. One thing I'd ask for everybody to do is to join us on LinkedIn. We do have industry guides and textbooks and best practices for instrumentation and gas flow measurement, and we'd be more than happy to make those available to you. So as I said, that's my presentation. I'm wrapping it up here, and thank you all for your time.
Adam, great job, man. Really good job. As if we expected nothing less. And I do have a question for you. So I hope you have a quick minute here to address this. So another issue that we see is wet gas. So what are some strategies for getting an accurate measurement if we're dealing with, say, significant moisture?
That is a very, very common thing that we and our sales partners run into. Our first guidance is use a knockout pot, use a dryer, utilize the technology that's available for knocking the moisture out of the gas. In certain situations, we have seen customers have very good results thinking about how they install our equipment. So for us, we've seen in practice that if you insert a flow meter from the top down, that moisture will essentially, gravity will pull it down and cause the moisture and the droplets to hit our sensor head. That'll affect our measurement. We found success in actually installing it at an angle where you make gravity your friend. So instead of the moisture dripping down and gravity pulling it down and having it throw your measurement off, letting gravity work in your favor. So that's number one. Number two, there are manufacturers out there. FCI happens to be one of them, who have made actual sensor heads that have the knockout drum essentially built in. So there are sensor heads with different instruments that are designed for moist gas that essentially will shunt the moisture in a moist gas or a wet gas application from hitting the sensor head. So the two answers to that: one, let gravity be your friend, install the meter this way, if you can see my hand. And two, do some research on the different sensor head options that are available. Some manufacturers have really done some great things to make offerings that will give a wet gas effective sensor head.
Good stuff. I think it's safe to say that if you have a question, FCI not only has the answer, but has two answers because they just know so much about the topic. So I appreciate you letting our audience know, and that's a lot of good info there. So Adam, much appreciated. Great job.
Thank you very much, Travis.